Hello everybody. So I will continue now on the lecture about mortality, and the topic now that I will discuss about is going to be life table. So with the life table we can estimate life expectancy at birth and for the other age groups that we are considering in our analysis. So let's just go to slide 29 to start this lecture. So one of the most important and elegant measures of the mortality experiences of population is the life table, because with the life table we do take into account the age composition of different countries, and then we can compare the life expectancy of these countries after we calculate them using the life table. So life tables date back to John Grant, who is known as the father of demography, as I mentioned before, and his bills of mortality. So his bills of mortality, that was pretty much when he was trying to understand death rates by age using vital registration data from London back in the 1600s. So he used that data, and he was one of the first people to start develop, or he was the first person to start to develop life tables. So demographers use this life table to determine life expectancy. And life expectancy not only at birth, but for any other age or age group that's being considered for the analysis that you collected data for. So like the total fertility rate, the life table is a synthetic or a hypothetical measure. So it will tell us how many years of life on average may a person expect to live if the person during his or her lifetime is subjected to the age-specific probabilities of dying of a particular country or population at a given time. So just remember, the total fertility rate was the average number of babies that we would expect that the woman would have if they were exposed to those age-specific fertility rates throughout their childbearing years. In this case here, life expectancy at birth that is calculated using a life table is going to tell us the average number of years that people would live if they were subjected to the age-specific probabilities of dying for a specific country in a specific time. So to give an example, let's say that the population in the United States in 2010 had a life expectancy of birth of 78.7 years. So this means that if a cohort of people throughout their years of life were subjected to the age-specific death rates of the total population in the US in 2010, they would live on average 78.7 years. So pretty much saying that you have to consider those age-specific death rates for all the age groups. If people were subjected to those rates throughout their lives, they would live on average 78.7 years. So this here are some examples of life expectancy at birth for several of different regions of the world and also for some countries. And life expectancy at birth is a primary indicator of quality of life. That's why it's so important. And because women, they have on average higher chances to live longer, so they have a higher life expectancy than men, we usually calculate life expectancy by sex, because life expectancy for men are lower than for women. So in the world in 2013, life expectancy for men was 69 and for women was 73. For more developed countries, 75 and 82, and less developed countries, excluding China, 65 and 69. And if you look at specific countries, we also see a lot of variation. In Japan, for example, 80 years on average of life for men and 86 for women. And for Lesotho and Sierra Leone, much lower levels, both for men and women. So before we talk about the life expectancy at birth, and life expectancy at birth, the symbol that we use is this E0. We just need to be aware of the fact that when we consider life expectancy at birth, infant mortality plays a very important role. So because life expectancy at birth takes into account the mortality rates for all age groups, including for the age group of babies between 0 and 1 year of age. So when life expectancy at birth is low, a major reason might be because we might have in that specific country very high infant mortality rate. So when comparing values of life expectancy at birth across countries, we should not think of life expectancy at birth as a model age at death. So we should not think as the life expectancy at birth as the age that most people die. Because in some countries, maybe the life expectancy at birth is being driven a lot to low levels because of very high levels of infant mortality rate. So we should just be careful when we interpret and try to understand life expectancy at birth. Another important thing is that we have to understand what are this concept of abridged life table. So an abridged life table is pretty much a life table that uses age groups instead of single ages. So usually we use 5-year age groups and rather than single year age groups for when we estimate life expectancies using life tables, because for some countries, information for single years might not be really reliable. They might have problems of quality. So we group them in these 5-year age groups so we have more reliable information. So whenever we are estimating life expectancies and like using life tables, we start with a population of people that will be born alive at age 0. A standard that we can apply is that we pretty much can always use 100,000 people that will be born at age 0, and then we will apply the age-specific mortality rates to these people here. So we get the age, for example, the age-specific mortality rates for Japan, the age-specific mortality rates for the US, and then we apply the same number of people to be exposed to those mortality rates. So this is an arbitrary number, but it's a conventional number that we use. But instead of 100,000, we could also use 1,000 or 1. But overall, what we have to do, if we are trying to compare different countries, you get the age-specific mortality rates for those two countries, and then apply for the same amount of people those chances of dying. From each age to the next, the population is decremented according to the age-specific mortality probabilities until all members have died. The mortality schedule is fixed and does not change over the life of the population. So we pretty much are applying, we get the age-specific mortality rates, transform them into age-specific mortality probabilities, and then we get this number of people here and apply to the mortality probabilities that we have in the life table. So here we have a life table for the US in 2010. Originally we get the mortality rates, the age-specific mortality rates, and with them we calculate the age-specific probability rates, which are symbolized by the QXN. And we have them for each one of the age groups, 0 to 1, 1 to 4, 5 to 9, and 100 plus. We have the 0 to 1 separated from 1 to 4 because 0 to 1 pretty much we have the information about infant mortality. So this is the probability of dying of people before they reach age 1. And then we have the Radix of the life table, as we showed in the previous slide. This Radix here will be the people that will be exposed to these mortality probabilities. And if this 100,000 people here were exposed to this mortality probability here, in the first age group, 612 babies would die. So out of the 100,000, 612 died, so 99,388 survived to the next interval. And this one's exposed to these mortality probabilities, we have 106 deaths, this number minus this number, we have 99,281 people surviving to age 5. So this column here is the number of people surviving to the beginning of the next age group. So the little lx has only the subscript x, doesn't have n, because it's the information of people surviving into the beginning of the next age group. So here is the number of people who survived to the beginning of this age group, to this age group that starts with 5. And 99, let's say another one here, 95,833 people survived to the exact age of 45. And this, so here we have the number of people dying within the age group. So we, in this case here, we do have the subscript n, because here we have 612 people who died in the age group of 0 to 1, 106 people who died in the age group that goes from 1 to 4. And this column here, the big L column, or in this case we do have again the subscript n, so it's the big LXN, we have the number of years that people lived within the specific age group. So some of these 100,000 people died in the age group. To be more specific, 612 people died in this age group. So in total, we had 99,465 years lived out of all these people here within this age group. So let's just say that nobody dies. Let's just say that the mortality probabilities here are 0 for everybody, so nobody dies. So these 100,000 people here, 100,000 would come here, 100,000 would come here, and so on. So let's see for this third age group. If we have 100,000 people here, and then 100,000 go to the next one, it means that all the people from 5 to 9, they all lived 5 years. The years of 5, 6, 7, 8, 9 years of age. So the big LXN column would be equal to 500,000. Okay, but because people die, we will discount it, and then we will have numbers that are going down exactly because we have people dying throughout those age groups. And if we get all this column here and add all this number of years lived by these people throughout these age groups, the total here of all these numbers is the TX column. So this number here is going to say the number of years lived by people from this age group until all the next ones, until the end. So, and just remember, another way to say the number of years lived by people within the age group is called person years. So the big LXN is also called the person years, the number of years that people lived in total within this age group. The TX is the cumulative, the overall number of person years lived throughout all these age groups. This one here, we start from this and then add up until the last one. 29,000 will be this 24,000 plus this one here. And then the last one is going to be just the last one here. And finally, you have the life expectancy for each one of the age groups. This one here is the E0, life expectancy at birth. But we also have life expectancy for each one, for all the other age groups that we are considering in our analysis. And in this case here, we pretty much get the overall number of years that people lived from here until the end. So we add all these people, get the big T0 here, and this number divided by the number of people that entered that at the beginning of that interval will give us the average number of years that these people lived throughout their lives, so 78.7. And This number here is the overall number of years that people lived from age 1 until the last one. And how many people entered the age group of 1 to 4, how many people were alive by age 1 is this 99,388. So this number here divided by this is 78.1. So what does this number mean? It means that conditional that the person reached the second age group, reached age 1, that person will live an addition, those people will live in an addition 78.1 years on average. So that means that that person gained another year of life, because here in this case it's going to be 78.1 plus 1. So these people on average will live a total of 79.1 years on average. And that's so because they passed the risk of dying from the first age group, which was high compared to these other ones here, then that person gains a bonus. And for example, in this age group here, 60 to 64, we have this 23. So we are saying that once people survive into this age group, they reach age 60. So these are these people here, they reach age 60, they will live an additional 23.1 years on average, additional to the 60 years. So it means that these people will live on average until age 83.1, because it's 23.1 plus 60. Okay, so the next slides just go into more detail, explaining each one of these columns, column 1, 2, 3 until column 7. So the one, as I mentioned, are the age intervals of each group. The QXN is the probability of dying between ages X and age X plus N. LX is the number of survivors at each age X at the beginning of that specific age group. DXN is the number of deaths between age X and age X plus N. Big LXN is the number of years lived by all persons who enter the age interval while they are still in that specific age interval. And the TX is the number of years lived by the population in the age interval and in all subsequent intervals that they will live. And EX is the remaining life expectancy at each age X, which is the age at the beginning of the interval. Going into more details about each one of these columns of our table. The age groups refer to the range of years between two birthdays. The age groups 5 to 9 refers to the 5th year interval between the 5th and the 10th birthdays, for example. So it includes ages 5, 6, 7, 8, and 9. The probabilities of dying is the most basic column of the lifetime. The most basic column of the lifetime shows probabilities of dying for each age group. So that's the QXN. These are probabilities that persons alive at the beginning of an age interval will die during the interval before they reach the start of the next interval. And we calculate them using the number of people who died within that specific interval divided by the number of people who entered that interval. So that's the number of people who were alive at the beginning of that age group. The number of people alive at the beginning of that age group is the little LX, and then we get the number of people who died throughout that age group divided by the number of people who are alive at the beginning of that age group. We get the probabilities of dying in that age group. And then for the last age group, in our case, in our example, is the age group 100 plus, so people who are at least 100 years of age. The probability of dying equals 1 because everybody dies. So 100% of the people will die. And just a little bit of discussion about the difference between probabilities and rates. The difference between the mortality rates and mortality probabilities is the denominator. Mortality rate symbolized by the MXN and the mortality probability is the QXN. For rates, the denominator is the mid-year population. For QXN, the denominator is the population alive at the beginning of the age interval. If we just go back to the previous slide, this is the population alive at the beginning of the age group. So that's the little lx. So that's the denominator of the formula for the mortality probabilities. When we get data, raw data from countries, we have the mortality rates for each one of the age groups. And the denominator is the mid-year population. So we have formulas in order to calculate the mortality probabilities based on the mortality rates that were observed for a specific country or for a specific state, for example, in a specific year. So based on this observed raw data, we calculate the mortality probabilities. And I will show you in the Excel table that it's available in the course website a formula that we used to make this transition here. There are different formulas that we calculate mortality probabilities based on the mortality rates, and I will show one of them in the Excel spreadsheet. So the number of people alive at the beginning of the age interval is known as the little L column, the little LX column, and it is calculated by subtracting the number of people dying in that specific age group from the LX value in the age interval immediately preceding the one being calculated. So we get the number of people dying in this specific age group minus the number of people who entered the previous age group, and that's how we get the little L column. So for the US, the example of the life table in 2010, of the 99,224 people alive at the beginning of the age interval 10 to 14, 70 of them die during the age interval that goes from 10 to 14. Thus, the value of people surviving to exact age 15 is 99,154. So it's 99,224 minus 70. So 99,224 people reach exactly age 10. 70 people died between ages 10 to 14. So we will have exactly this number of people reaching exactly age 15. So that's how the little L column is estimated. And the number of people who died during a particular interval is estimated as being equals to the little L column times the probability of dying in that specific age group. So for the number of people who die during the age interval of 40 to 44, that's how we get that information. The number of people dying between the ages 40 to 44 equals the probability of people dying in that same age group times the number of people who entered, who were alive at the exact age of 40. So the number of people dying in that specific age group equals 966, using the example from the previous table for the US in 2010. The big L column is the total number of years lived by all persons who enter the age interval while they are in that specific age interval. So this is known as the big L column. And for that same example of the US life table in 2010, we know that 98,011 people were alive at the beginning of the age interval 30 to 34. That's based on the little L column, the little L 30. If none of them died during the age interval, they would have lived a total of 490,055 years. Because we would get, if nobody died between the ages of 30 to 34, and we know that 98,011 people were alive by age 30 and nobody died, we would have still the same amount of people by age 34. So we would have a total number of years lived by these people here equals this number times 5, which is exactly 490,055 years. But we know that 539 people died between these ages, between ages 30 to 34. So you have to discount that. Not all these people lived all the 5 years here between 30 to 34. Some of them died, so we have to discount that. So the big L column is going to be smaller than this number here. So demographers assume that deaths are roughly distributed equally during the 5-year period for many of the age interval. But this assumption does not apply to the first few age intervals, because usually for younger, like in the group, for example, from 0 to 1, most of the babies that die, they die closer to age 0 than to age 1. So there are several formulas to produce the big L column for the first few age groups, and I will show them in the Excel spreadsheet that's available in the course website. I will show it at the end of this lecture. At the other age extreme, the 100 plus in the life table, another formula is also used to calculate the overall number of years, because we don't know what's the final year that these people were living. So because it's an open-ended interval, so there is a special formula for the big LXN in that last age group. So the total number of years lived by the population in the age interval and in all subsequent age interval is the TX column. So we pretty much sum the big L column from the oldest age backwards to get the TX. So that's the notation to calculate the TX. And the LI here is the entry I in the LXN column. And we are summing from that specific age group that we are talking about, that we are taking into account in the life table, until the last age group, until the last entry of the big L. And just to show an example of how to calculate the big TX, this is an example from the same life table that I showed before for the US in 2010. For the T in the T95 in the age group that goes from 95 to 99, we get the number of years lived in that specific group from 95 to 99 plus the number of years lived in the following age group, the 100 plus. And these are the numbers that we get from the life table, 24,000 and 4,500. We get a T for that specific age group equals to 29,212. And then we have the column for life expectancy, which is the average number of years of life remaining at the beginning of the age interval. It provides life expectancy at any age. So we don't calculate only life expectancy at birth. We calculate life expectancy for all the age groups that are being considered in our table. And since we have age groups, that's why I'm talking about age groups. If we had a life table for single ages, we would have the life expectancy for each one of the single ages. So for the US, again, for the life table in 2010, the life expectancy at birth, we get the T0 divided by the little l0. We have people, if they were exposed to all those mortality probabilities throughout their life, they would live on average 78.7 years. And for the life expectancy at age 25, it means that once people survive up to age 25, they are expected to live an additional 54.7 years on average. So these people will live on average up to age 75.7, because it's 25 plus 54.7. So this person's age 25 to 25 can expect to live an additional 54.7 years, because they already passed all the risks of dying before age 25, but they survived. So they get a bonus. So now, instead of living only 78.7 years on average, they will live 79.7 years. This number plus 25. And this, the average age at death. The life expectancy is the expectation of future life beyond age X. It is not an average age at death. And we can add the information of the X, which is the age at the beginning of each one of the age groups, and the life expectancy for that specific age group to obtain the average age at death for cohort members who survived to age X. And that's exactly what I did when I was interpreting this number here, when I added this number to 25. So not all life tables include this column here. The X plus EX column always goes up in this case. So in that previous example that I showed you here now, I get 54.7, added to this is 79.7. So this is the average age at death for the cohort members who survive exactly until age 25. So that's the interpretation. And the life expectancy not always goes down. It often goes up after the first few years of life because babies who survive infancy are no longer subject to the high risks of infant mortality. Exactly because infant mortality is high, the probability of dying between ages 0 and 1 is high for some countries. The life expectancy does not always go down because it can go up from the first to the second one because of high levels of infant mortality. But this other column, the X plus E, always goes up. And these are typical shapes of the lifetime functions. So the probabilities of dying, they're usually high for babies below the age of 0, and then it drops, and then it starts going up again for older ages. These are the number of people dying. Each one of the age groups is high for young people, and then it starts to increase, and then it reaches a certain age where you don't have as many people left. The probabilities of dying are high, but the overall number of people is not so high, so the overall number of people dying in these more older age groups tends to decline after you reach a specific point here in the life table. And these are the number of people surviving to the beginning of that specific age group. So in our example in the life table, we had 100,000 as the Radix, but as I said, we could have also 1,000 or 100 or even 1. So here in this case, we have the proportion of people alive to that exactly age, and it starts from 1, proportion 1 or 100%, and until everybody dies. And the life expectancy at age X, it can increase a little bit from the first to the following age group, exactly because of high levels of infant mortality here. And once the children survive, they pass that chance of dying and they survive to the next age group, so the life expectancy remaining goes up, but then it starts to go down again. And with the life table, we can do a lot of different exercises. And Alfred Lockton, he used the life tables in the development of his stable population theory. And the stable population theory is the idea that, let's say that we have a population that, let's just consider a closed population. What is a closed population? A population that I'm not taking into account migration. I'm not taking into account people entering that population or leaving that population. So I'm not taking into account immigration or emigration. And let's say that that specific population has age-specific fertility rates and age-specific mortality rates that have been constant through time. Because let's say that mortality decreased so much that now the levels of mortality are really low, and the fertility rates also decline, and we have around a total fertility rate of around 2 children per woman, but has been stable over time. So if that population doesn't change the age-specific fertility rates and age-specific mortality rates, and we do not consider migration, this population will develop a constant age distribution. And it will grow at a constant rate, irrespective to its initial age distribution. So, and this I can show you with like the age-sex pyramid that I'm going to show in the following slides. In the following slides here, I have some extra information about life table from a different textbook. So I'm not going to go through in detail about each one of them, so I'll leave these for extra reading. And in this case here we have the life table for US woman in 2010, and then this here, for example, is a formula in which we calculate the probabilities of dying based on the mortality rate. So we have the mortality rate, and then with that we estimate the mortality probability. And so these are similar formulas that we have before. This is just to show the formula for the big L that for the last age group we have a different formula, and I'm gonna just go show you these formulas in the Excel spreadsheet in a moment. And one important thing here for these slides is this thing here. So far we interpreted the life expectancy from life tables with the synthetic cohort approach. So that's the lifetime mortality experience of a single cohort of newborn babies who are subject to specific age-specific mortality rates. So if a group of people, a group of babies, were exposed to those age-specific mortality rates throughout their lives, they would live on average the life expectancy at birth that we calculate from the life table. So that's the synthetic cohort approach. The stationary population approach, it's related to the stable population that I just mentioned before. So let's say that we have a population that the age-specific mortality rates are not changing, and we also have unchanging age-specific fertility rates. So we have a constant annual number of births and deaths, so which is pretty much the little L0, the radix of our table. So in that case, we will be able to get information from our life table if we consider that the age-specific mortality rates and fertility rates are not changing over time, that we will tend into this population that can be measured with an age composition that can be shown with the big L column. So let me just go further here to the big L interpretation. So here, what is the big LXN that I talked to you before using the synthetic cohort approach? Is the number of person years that would be lived within the indicated age interval by the cohort of 100,000 births that we assume in the radix of the table. The stationary population approach, the big L column, is the number of persons in the population who at any moment are living within the indicated age interval. So if age-specific fertility rates and age-specific mortality rates are stable over time, you would expect that you would have that number of people in each one of the age groups as expressed by the big L column. So here it's the life tables estimated for the US, in this case here for 2007, and this is for women and this is for men. So this big LXN, the big LXN column, if it's reasonable to think that the age-specific death rates are stable over time. These numbers here, when I say that the age-specific death rates are stable over time, I'm saying that these numbers here are not changing much for the next years. And we are saying that the age-specific fertility rates are not changing much over time. So you tend to have around the same number of people being born in that specific country. So these numbers here will be the number of people in each one of these age groups from now and forever, if those rates don't change. So what's the real population in the US in 2007 by age and by sex? We get this column here, the population by age and by sex, women and men. We get this number here and put in a percentage format and put in the age-sex structure in a graph format. This is what we have. We have more people in younger ages, in adult ages, than in older ages. But let's say the age-specific mortality rates are being stable, and also the age-specific fertility rates. So let's just go back a little bit. So we'll get these numbers here by age group for women and for men, and express it in percentage format, and put in the same age-sex structure for the population. So the first one here is the next slide. And then this one here is this age-sex structure. So what we are saying is that if the age specific mortality rate and the age-specific fertility rates do not change much in the US from 2007 to the future, this would be the age-sex structure in the US for the coming years. So you tend to have more people in older ages because they're surviving more, and you tend to have a more rectangular shape. So that's the importance of the life table, because if you have a society that in which the mortality, the age-specific mortality rates and the age-specific fertility rates are not changing much, we can kind of like think, use the life table to do some population projections. Okay. So so these are the slides related to life table, and now I'm going to show you the life table in Excel. So this Excel spreadsheet is available in the course website, and here I got some raw data about number of deaths and population for each one of these age groups for women and for men, and I put here the source of data where I got it, the website from CDC. I organize a little bit this data to put them in the format that we need for the life table, for women and for men, deaths and population by age group. And then I have the life tables for women and for men. So this column here, the AXN, I had not talked to you before in the presentation, is the average years in that specific interval, the average number of years that people live within that specific age group. So from 5 to 9 until 75 to 79, we are saying that on average, people will live 2.5 years. So from 5 to 9, we have 5 years. From 10 to 14, we have 5 years. So we are saying that people are dying, those who die in that specific age group, they will die on average kind of like equally distributed in the interval. Some will die at the beginning, some in the middle, some at the end, in the same pace. So on average, those who die, they will live on average 2.5 years. And that information is important, the AXN, because with that, we will estimate the big LXN column, which is here. Because we're pretty much saying those who survive to the next age group, the little LXN, they lived all the width of that interval, which was, for example, here 5. But for those who died, they died around 2.5 years within that specific age group. So they lived around 2.5 years. So that's why this information is important. And that information is also important to calculate the probabilities of dying. So here we have the average years in the interval, the AXN, the population that we got from CDC, number of deaths that we got from CDC by age group for women. This number of deaths divided by population, the age-specific death rates, which is this number here, is the number of deaths divided by the number of population. And the time here in this case is 1 year, so that's why it's pretty much the D divided by the K. And we calculate the QXN, which was the column that I showed in these slides. So in order to reach this, we have to implement this formula. So we are using mortality rates in order to estimate mortality probabilities. And we take into account the width of the interval and the average years that people live in the interval. So this formula here is the one that I write in this column. And then the LX is the number of people alive at the beginning of the interval. It starts with 1,000, and then we apply 1,000 with this probability of dying, we have this number of people surviving. And I'm just pretty much using these formulas here. This one should be more specific. And then number of people dying is going to be number of people who enter that interval and the probability of dying within that interval. So these are a number of people who died between the ages of 1 and 4. And so that's exactly this formula. And the big LXN, we have this formula here for all these different age groups up to this one here. So these formulas here, I'm implementing this. I get in the first age group, this is the number of years that people lived, those that survived to the next one, so this one times this, and those who died lived on average only 0.1 years. And for this one, we know that these 99,406 people who survived to the next age group, this one here, they lived a total of 4 years in the previous age group. Those who died, they lived on average 1.5 years. Next one. Those ones who survived to the next age group, the LX plus N here, 99,353, they lived a total of 5 years each one of them. So it's 5 times this. So that's this number here. And those who died lived on average 2.5 years. So that's the portion of the formula. So you see that for the first 2 age groups, something that I mentioned before, the average number of years, it's calculated in a different way than for these other age groups here. Because for these two, for those children, babies and children, or babies who die within that interval, they will die closer to the beginning of the interval. So babies who die between the ages of 0 and 1, they will die closer to age 0 than to 1. Babies who die, or children who die between ages 1 and 4, will die closer to 1 than to 4. And that's how for the first group here, we calculated based on information of infant mortality, and the infant mortality is this cell here. So we're pretty much implementing this formula right there. And from 1 to 4, based on empirical data, usually we assume as being 1.5. Children who die between ages 1 to 4, they will die closer to age 1 than to 4. And for the other ones, we pretty much just get the 5 divided by 2, which is what I mentioned before. We assume that these people are dying. The pace of dying for those who die will be similar across the age group, within that age group. And for the last one, we use, it's pretty much 1 divided by the last mortality rate here, and this will force the probability of dying be equals to 1. So with that, we calculate the big LXN column, implementing this formula, and the T, we just cumulate, we just sum all these ones, for this one, for example, all these ones, for this one, we all that. So that's the formula here. Life expectancy is the Tx divided by the little lx. That's the life expectancy, so we do the same for all of them. The average age at death, we get this one, and we add to the age at the beginning of the interval here. So for example, for these people here, those people who survived up to age 50, so conditional on people survive to age 50, those who survive to that age will live an additional 30 years. So on average, they will live 80 years. So they will, once people survive to age 50, they will live on average 80 years of age. When we're talking here about the data from the US 2017, and we are talking specific about women. And this is just another column just to check if the calculations were correct. So this column here equals this column here. Should be equal, so we had not done any mistake. This is the life table for men, same idea. And then I just get this population here for men, and then the same thing for women to generate this age sex structure of the population. And then for these two life tables, I get this column here of the big LXN from here and from here, so 99,434. Sorry. Oh yeah, because like here for the first age group there, I added these two, but let's just see for this one here, 5 to 9. The result was 496,227, which is gonna be exactly this number here, 596,227. This number here adds 0 to 1 and 1 to 4. So that's the 0 to 4. So we get this information, transform into percentage, and that's that graph that I showed you in the PowerPoint presentation. Okay, so that was the lecture specifically about life table. So thank you very much.